Okay, I'm going to walk through how to do a connectivity analysis using the fNIRS data. So there are two distinct pipelines that we use to do the connectivity analysis. The first one is correlation based. So the first thing that we would do for that one is load in data that has a low pass filter. We use a cutoff of 0.2 hertz. And then we also apply selective motion correction to these participants only if their data has motion artifacts. So if you're doing the correlation analysis, you'll pre-process the data in that way or a similar way, and then you'll load it in. Um, then what we do is pretty simple. I have a for loop here that goes through, and all it does is it creates a correlation matrix for each of the channel pairs. So this is a 22 channel device. This is going to create a 22 by 22 matrix with the Pearson's correlation between each of those, any two given channels. All right, so that's the first thing that we do is we create that 22 by 22 correlation matrix. I save those as MATLAB variables. And then our second pre-processing and analytical pipeline is a coherence-based analysis. We actually pre-process the data in a different way for this one. So for the coherence analysis, we actually use bandpass filter. The range that we have used to do that is 0.01 hertz to 0.2 hertz. And then, of course, we still selectively apply motion correction. So when you're ready to do the coherence portion of the analysis, you'll load in the data that has motion correction and a bandpass filter. And then what you will do is you will calculate the magnitude squared coherence between each of your channel pairs. So I have this commented out because I had just ran the correlation, but you can see. Okay, so here is the line of code that we use to calculate the magnitude squared coherence. So as you can see, we use a for loop to grab two of the 22 channels, and then we also tell it the sampling rate and then the number of samples to use for the Fourier transform. So assuming you're working with the same device, this is probably the same way that you do it. Otherwise, you would probably change these parameters. So anyways, once you've done that, then you'll be left with a some matrices that contain the magnitude squared coherence at different frequencies. So in order to turn that into a 22 by 22 matrix, just like the correlation matrix, what you're going to want to do is for each channel, take the average between the frequency range that you're looking at. So yeah, that's what you'll do. Then once you have your 22 by 22 matrices for both the correlation and the coherence analysis, you can take that a step further and look at some graph theory outcomes. So there is an open source toolbox that we use called the Brain Connectivity Toolbox. You should just be able to Google that and download it. I think it's available in GitHub, if I remember correctly. So you're going to want to make sure that's installed on your computer. We use a threshold of 0.5. So what that means is that any channel pair that has a correlation or coherence value greater than 0.5, we consider there to be a functional connection between those two channels. This is a pretty standard cutoff for fNIRS data. It's usually a little bit lower for fMRI data, but you can always refer to the most recent literature if you are not sure about what kind of threshold you should be using. So the brain connectivity toolbox has a ton of different graph theory metrics that you can compute. Depending on which ones you want to explore, the best place to look into that would be the brain connectivity toolbox user manual or any forums that are online for it. We specifically wanted to calculate degree, the clustering coefficient, betweenness centrality, and efficiency. When we were first starting this, we didn't know if we wanted to look at it channel-wise, region-wise, or the average across all channels. So I average in a couple different ways in this script, but ultimately what we prepared for a publication was to look at region-wise results. So that might be a good starting place for anyone else doing a similar kind of analysis. So the first thing that I do is I set the diagonal of each of my 22 by 22 matrices to equal nan. That's because the diagonal is where the correlation or coherence between one channel would be stored. So for instance, the correlation between channel 1 and channel 1, the correlation between channel 2 and channel 2, etc. So obviously for every channel pair along the diagonal, the correlation and coherence would be perfect. So if you're doing any kind of averaging, that's going to kind of inflate your results. And then also from a graph theory standpoint, you might not want that included in your network. So we set that to nan. Then we create our adjacency matrix by looking for values that are above that threshold. So we want to see where those functional connections are. And then all of this that I did here to calculate these metrics, I learned about from the Brain Connectivity Toolbox user manual. So this is just how you do it. And of course, it might also be worthwhile to explore some additional ones that aren't shown here. For our results, we saw the best between group differences using betweenness centrality and degree. So if you're reading any of our publications, that's probably what we're talking about. So yeah, that's it for the connectivity analysis.